Good afternoon, part 2. The content in my lectures generally can be found in textbooks. In fact, the material that I teach in my courses have been known for decades, if not for centuries. Well, the material that we're covering right now in this subject is such a current and active area of research that I'm learning this the same time you are. In fact, there are peer-reviewed journal article papers that are published right now, last month, last week, on these sorts of problems that we're covering today. It might be slightly more involved in the peer-reviewed journal papers, but morally, if you cut to the core of what those authors are asking, it's conceptually the same types of questions that we're asking right now about developing a model using experimental or simulated data. So, I'm learning new things the same time you're learning them, and I'm discovering really cool, fascinating things as I learn this new subject area. And I'm so excited to share some of the new discoveries that I've had in this subject of trying to incorporate data-driven models in our science and engineering research. And I wanted to use a problem that we're very familiar with, and I've been covering in a lot of my courses over and over again. That is the heat equation, a very well-studied problem in science and engineering, but with an interesting twist related to data-driven models. So let's suppose that we have some complicated material, and we would like to develop a model for heat transfer inside this material. So ultimately, our goal is to develop a model that takes in position x and time t and spits out the temperature inside this material as a function of position and time. Now, for simplicity, we're going to use a 1D model that runs along the x direction from position 0 to L. And for simplicity, we're just going to set the length of this material to be a unit of 1. Now, again, for simplicity, we're going to use Dirichlet homogeneous boundary conditions, or zero temperature boundary conditions on both ends. Now, this is a very, very well-studied system. It's probably bringing back nightmares from when you first learned separation of variables and the 1D heat equation. Yeah, it's exactly that, except there's a twist. Inside this material, there's some kind of heat generation, some source of energy. Maybe it's an electrical wire that runs across your composite polymer and it's generating heat through its electrical wire dissipation. So it's heating up your material. Or maybe there's some kind of chemical reaction happening inside this polymer film that's exothermic and it's generating heat and injecting heat into the surrounding polymer film. So there's some electrical wire inside your material and it generates heat. And that source of energy we're going to describe as some function f that depends on both position x and time. So the key point here is note the dependence of this heat source on both the position and time. And you can imagine that would be true in a real material. You can have an electrical wire that isn't spatially homogeneous. It might generate more heat on the left end compared to the right end. So then it might have some spatial variation in how much heat is being generated locally. And it can also be time varying. If it was a chemical reaction, or even for electrical wire, the wire might get older and older, or the chemical reaction might have some transient process to their exothermic heat release. And therefore, at any given position in space, it can also be a function of time. So the heat generated inside this material is in general both a function of position and in time. Now, if you were to write down the governing equation for developing a model for how the material temperature behaves as a function of position and time, you might run straight to the conservation of energy, because that's exactly what we've been covering in a lot of our lectures. It would look something like this. This is the 1D heat equation with our heat source F as a function of x and time. So the left-hand side is accumulation. This term is your diffusion term. Alpha is your thermal diffusivity. And lastly, we have our generation. And a lot of times, this source is often called a forcing. It's a forcing function that is forcing the equation. So sometimes I'll say forcing throughout this lecture. It's just some heat generation that's being injected inside your material. Now, we have solved this equation, this heat equation, without the forcing term in so many different contexts. Different boundary conditions, different initial conditions, different boundary geometries, domain sizes. So this term over here, the accumulation equal diffusion, these two terms over here, you have solved in so many different contexts in your past classes or past lectures. Now, if you're a little bit rusty on that material, definitely please go back to my lectures where I follow along step by step on how to solve this heat equation or the diffusion equation in various different contexts, different domain geometries, different lengths, different boundary conditions, different initial conditions. A lot of what I'm going to talk about today and in next lecture is going to be predicated on the fact that you know how to solve the heat equation using separation variables, using Fourier series. Those types of concepts need to be solid in your head. All right, so you would know how to solve this equation, but in real systems, in real applications, you don't know what this forcing function is. So this term might be completely an unknown entity to you because it's electrical wires in your material and you have no idea how it depends as a function of position and time. Or it's in a chemical reaction that you don't really know how to describe, and therefore this forcing function is completely unknown to you. So in most of my applied mathematics courses, I teach you how to solve this equation with a known terms, right? So we know the accumulation term, we know the diffusion term, we know the functional form of f as some function of position and time. If you give me this f, let's say f is equal to x times t squared, a specific functionality, then I can teach you how to solve this equation. That's the crux of a lot of the applied mathematics that we teach you, both analytically, numerically. There is a whole set of techniques on solving this equation when this function is known. But, like I said, in a real research application, we don't know what that forcing function is. And as an experimentalist, though, you can stick a thermocouple inside your material to get very good data or measurements of your temperature. So, suppose you go out there and you have measurements of your temperature. You know T as some function of position and time because you stuck a thermocouple inside your material, measure the temperature as a function of position and as a function of time. So you have measurements of that. And you kind of know as a scientist and engineer that it must be solving some kind of energy balance. So the governing equation might look something like this. So as a scientist and engineer, you have a guess that this must be the correct model that the system is actually solving. But you don't know what this forcing function is. So that's where a lot of what I wanted to cover today and next lecture is about how to incorporate data-driven models with some knowledge and physics knowledge of the heat equation and take those two separate tools together to make progress in developing a model that is transferable, that you can use and you can trust. So let's first state our given and our goals of this problem. So the given is, as an experimentalist or as a simulator, you have access to temperature data. So you have data on the temperature as a function of position and time, but in a tabulated form. So the data that you've collected might look like a matrix. All right, so the data that you collected might look something like this. You have a measurement at time t equals 0 across your entire domain from x going from 0 all the way to L, which in this case is set equal to 1. So you have measurements that go along this row at initial time. So you'd have numbers that all fall along here. Okay, that would be your thermocouple measurements along the entire length of the material at a given time, t equals 0. Now you take one time step forward to t equal to 1, and you make the same measurement at the same positions. And you repeat this experiment over time, all the way to your final time, tf. All right, so you have this gigantic 2D matrix that contains all your data. They're just numbers, okay? They're just numbers that fill up each entry of the matrix corresponding to a particular time point that you measured at and a particular position along the slab. And that's all you have access to. All right. So our goal is to develop a model that you can use and predict the temperature inside this material. So our goal is to develop a model that maps some position and time to a temperature. Just like we've always been doing in all of our classes. When you solve the heat equation, the 1D heat equation, at the very end, you're going to get temperature as a function of your inputs, position and time. And for a Fourier series infinite summation, you get a summation. It's going to have e to the negative eigenvalue minus eigenvalue alpha times time t. That's your temperature, time t dependence, times a bunch of sines and cosines that have an argument x inside them. So that is a model that maps a particular position and time to a temperature. That's all you've been doing all along. And you've been developing models because you knew the governing equation and you were marching forward from the assumption that the governing equation is true and you know all the terms and you march forward and then boom, out comes a model. Now, this is a totally different way of approaching the problem. You don't know the full equation because you don't know what F is. But you do have data on the measurement. So it's almost like your experimental measurement is actually doing whatever it needs to do with an actual hidden mystery function f of x comma t. And then as a result of that, boom, it's outputting data, which is what you have access to. So it's kind of a frustrating situation where you actually know, you have measurements of the true phenomena, but you don't know the model that produced that phenomena. So it's kind of like an inverse problem, right? It's a totally different way of thinking about it because you want to get this model, but then to get this model, you have to solve this equation. But to get this equation, you don't know all the terms, but you have data that is the outcome of whatever term is supposed to go there. And actually, this frustrating situation I just mentioned is life. That's just science and engineering research that happens all the time. So how would we go about developing such a model? So in a real research application, like I said, this data matrix would just be raw experimental data. You would just collect them out in the field and you would have this data. But for today, for the practice problem we're going to talk about now, I'm going to generate simulated data using a prescribed function for f, x comma t. And I'm going to solve this equation that will produce a bunch of data here. And we're going to take that data and now assume that I no longer have knowledge of f and try to get a model for x and time mapped to temperature. So that's often called simulated data sets. You start with some known function you're inputting. You're generating results based on solution to this PDE. You can solve it numerically, whatever. There are many methods to solve a PDE. You solve it using some prescribed form. You get some numbers. You use that number as if you didn't know that it came from that forcing function. So that's a very common way that researchers will generate simulated data to develop a model and to practice them. It's kind of like a control study using a very well-controlled environment where you actually know the answer, but you assume that you don't know the answer. Okay, and we're gonna show 3 different cases of simulated data today with varying difficulty levels. So first, I wanted to show you what case number 1 looks like. So let's go over to the screen. I wanted to show you what the simulated data looks like. So what I'm doing here is loading this data set, Fourier heat final.mat, which contains our simulated data. So what I've done is I've prescribed a forcing function shown here, f x comma t, that's our forcing function, that's the heat generation, has a term here that looks like sine pi x times cosine 2 pi t. So it has a single mode in position, sine pi x, and it's got a term that's multiplied with a time-dependent function, which is also periodic. Okay, so that's our prescribed fx comma t. I've put that into this partial differential equation, solved it, generated a bunch of temperature data, and that's what's shown here in the data. So let me just execute this section up until here. Just gonna execute that one. Okay, so now if we go over to the workspace, you can see what we have here. So from the data, what it contains is, first of all, the positions x. So let me just show you x. So here are all the spatial positions. You can see here it starts with x equal to 0, and it goes all the way, it continues all the way to L equal to 1. Okay? So you can see that the position goes all the way to 1. Now, the next variable is time t. So let me just show you that as well. So t goes from 0, it continues on all the way to tf, which is the final value, which I've also set to be equal to 1. And you can see there are 100 discretization in time, and there are 50 discretization in position. So you have a data set of 100 time points and 50 spatial points. And at each of those positions and time, we have the true temperature profile, which is stored in this variable uTrue. So let me just show you that as well. That's right here. So you can see there's this gigantic matrix that goes down in rows to 100. So that's 100 time points where I've taken the measurement from time t equals 0 to tf, which is set to 1. And if I go across in column, you can see it goes all the way to a column of number 50. So there are 50 spatial positions discretized along my material. So it is a 100 by 50 data set. And each of these entries, you can see here, 0.0057, 0.0075. Each of those are temperatures at that particular position and time. So, like I said, this is a very realistic situation. Suppose you've done an experiment, you have an entire data table of the temperature that you measured as a function of position and time. Now, I've also set the thermal diffusivity to some value. I think I set it to 0.01, and that's what we have. So, as of now, this is what you have. Like I showed you here, back on the board, this is the given temperature data. Position x, 0, all the way to L of 1, time t equals 0, all the way to tf, you have 100 by 50 matrix of temperature measurements of your material. This is all you have. That's it. So how would we develop a model from the list of numbers, a gigantic 2D matrix of numbers that I just showed you? One approach is to do what I called last time in my part 1 lecture, a black box model, which relies entirely on a computer in a neural network and machine learning to develop a model for us. In that model, what we're going to do is we're going to take in inputs, which is position and time, and it's going to output temperatures based upon the training data that I just showed you right now. So we're going to use the data that you just took as the training data that the model can learn the right neural network parameters such that it will map the position and time to the temperature that I'm going to feed it. And if it trained properly, it should be able to map at a particular position and time. I can spit out my particular temperature. So let me show you that. Okay, so on the screen you can see how I'm setting up this black box model. This is everything here I just shown you. I've extracted the position, time, the true temperature value. It's got dimensions n sub t by nx. It's 100 times 50 in this particular case. I'm gonna create a mesh of position and time t, and those are my inputs. So you can see here, inputs to the neural network is gonna be my list of positions and list of time points t. So this is gonna be a 2 by nt times nx matrix. Let me just show you that right now. Let me just evaluate that. So let's take a look at our inputs. So here they are. This is like I said, a 2-row matrix. and it is 5,000 columns long because it is the total number of time points, which is 100, times the total number of spatial points, 50. Essentially what I've done is I've taken my x positions and time position and created one gigantic matrix that has this format of 2 by 5,000. Okay, so this is all the inputs. All it contains is my discretization of position and time. That's it, just a list of numbers. Now, my targets right here, which is the training data, is again my list of numbers for the true temperature values. So my target is just a single row vector of 1 by 5,000 that corresponds to all my temperature values at that particular points of my input. So if I go to my input, and if I go to, for example, row number 1 at entry number 6, that's corresponding to a particular time and particular position. My target at that point, 1, 6, is a value of 0. So it's saying at that particular time and position, it's got a temperature of 0. So it's just a rearrangement of the gigantic 2D matrix as just one gigantic row vector. All right, so it's just a 1 by 5,000 vector. And in MATLAB, I'm just going to use this simple feed-forward neural network. If that doesn't mean anything to you, don't worry about it. It's just a particular simple neural network architecture. And I'm going to put 2 layers in between, each with 50 nodes. Okay? And this train built-in command will take in this model that I've set, which is a feed-forward network, and it takes in my inputs here. So this input is literally my 2 by 5,000 vector matrix, and it's taking in also as an input the targets, the data that you collected. It's taking in both of those, and it is going to do an iteration inside this built-in function to optimize this model net. So at the end of the day, this function net contains our model. That should contain, for a given position and time, what's my temperature. So it's going to be a model, a function, that will produce a temperature from a given position and time. Let me just draw on the board what we've done here. So graphically, what we have done is we've taken our inputs, which were a vector of time points from 0 all the way to TF, and a bunch of spatial points from 0 to L. Those were our inputs into our neural network function called net. And our output is going to be temperature. Now, for our training data, we used the simulated data, which was a gigantic matrix of the temperature at position 0, time 0, all the way to temperature at position L, time TF. Now, the neural network, through the built-in function, is going to have a guess for the relationship between time and space to the temperature. It's going to compare the error of that guessed parameter set with the data that you've provided. It's going to iterate and fix all of its combinations of parameters inside this neural network function called net, and optimize all the nodes connection and all the parameters such that we have a good mapping from time and space all the way to temperature that agrees with our data. It minimizes the error between the training data and the actual model that you've provided. Okay, so let me show you what that looks like in code. So if you go back to the screen, you can see here that this is where we are training the network, okay? So we've just showed you that we're training. At the end of the day, we have this entity net, which presumably contains our model. So now if you wanted to actually produce solutions coming out from that model, you can actually just say net is an argument of whatever space and time that you've provided. So you know how in MATLAB, once you have a function, you could just send in your arguments into that function, and out comes your outputs. That's exactly what we have. So this thing net, right, which was trained as a part of this process up here, now contains our model. It will map space and time to an output. And I've labeled that as U prediction because now that's the predicted temperature at the particular input values that we've put in of space and time. Now, all we're gonna do is we're gonna plot this against the true result. So what I'm doing here is just putting an animation where I'm gonna plot as a function of position X, the true values based upon the simulated data that we generated, and also the predicted value based upon the neural network model that it learned. Let's just first train our model. So right now it's executing this top section. So you get this neural network training window that pops up. This actually tells you the training process. I think you can click on some of these diagrams and it will give you the architecture. So it's saying I have two inputs coming in. There's a small little two there that you may not be able to see, but there's two inputs, time and space. It's going through these hidden layers, each of 50 nodes big, 50, 50, and then one output layer. And there's a little tiny little one right there that indicates that you have one output, which is temperature. So it's taking in two variables, time and space, and it's outputting temperature. So this is the architecture of our model. Now, let's go back to here. So now it just finished completing. You can see here that training finished, reached minimum gradient, and there's a bunch of other push buttons down here that'll show you the actual training process. Let's not care about that now. It also tells you about the actual minimization and the specific training algorithm it used. Let's not worry about that. But now, this net contains our model. We can evaluate the inputs and have an animation. So here's our animation. What I'm plotting here is the temperature along the y-axis as a function of position spatially. And we're gonna plot this at select time points, and you can see that as an animation. The black curve is the true data. As an experimentalist, that's what you collected, our simulated data. And the red dashed line is our black box neural network. So let's see what that looks like. Okay? So of course, we know the answer in this particular case because we put a periodic forcing for our function f of x comma t that's got sine pi x and cosine 2 pi t. So you can see that it's got periodic oscillation up and down, but also periodic along x and along 0 and position L at L equal to 1. So let me just play that again. Once more. All right, so what I wanted to talk about is a couple of different things. First, you can see that it agrees very well. The red curve, the dashed line, which is our neural network model, the model that we learned here through the training, and the black solid curve agrees very well. That means that it has learned the right neural network model that can map time and space to a temperature over the limited data set we gave it. Now, like I showed in part 1 of the lecture, it's going to extrapolate very poorly because it doesn't know what's happening before that time you started making a measurement or after that time. It doesn't know the specific details of the domain. So it's going to extrapolate and translate very poorly to other situations. And that's kind of expected because this neural network model doesn't know any physics. Zero. It's just taking in a list of numbers in a bunch of numbers going out. It has even no idea. Let's just back up even more. It has even no idea that the thing you're feeding in is time and space. So technically, it doesn't even know these things. I'm going to erase that because technically, all it's seeing is just a list of numbers in and out. I'm just going to erase all these things. So, from the eyes of the neural network, it's just seeing this. If I just showed you this with zero context, you would have no idea what I'm talking about. You'd have no idea what this vector is or what it even represents. It's just two vectors with a bunch of numbers. That's all it sees coming in, and then out comes a bunch of weird numbers going out. That's all it knows. It does not know it's solving a heat equation. It does not know anything about diffusion, accumulation, heat generation. It knows zero physics. All it's doing is detecting a pattern. It's a pattern recognition of numbers going in, numbers going out. That's it. It knows zero physics. Therefore, it is most definitely violating conservation of energy because it doesn't know any physics. It doesn't even know that it's supposed to satisfy conservation of energy. And it probably doesn't even give you, well, in some situations, it might give you very aphysical solutions. In this particular case, you might not have seen that as obviously, but you can get negative concentrations or very aphysical results that don't make any sense. Once again, it doesn't care that it's violating fundamental laws of physics. It's just seeing a list of numbers coming in, a list of numbers coming out. So like I said, it's likely very poorly transferable. If I make the smallest change in the thermal diffusivity alpha, if I were to change the domain size and double the domain, if I were to make the smallest little tweak to the system, the model that I just developed is not going to transfer well to that model. Right? If I were to just, for example, say, I'm going to change my thermal diffusivity to twice the value. Can I use that exact same model that I just trained here and expect me to predict temperature? No way. No way. It is not gonna extrapolate well to the minor tweak that you put into your material. So while it did interpolate well, like you just saw in the video, it's just not a very useful model. So yes, it did develop a model from position and time to temperature. It's just not useful at all. Because as a scientist and engineer, you want to be able to take a model and then predict material properties and design new materials that you don't have a training set for. So why would you do this process, right? It doesn't make much sense in this particular case. All right, so let's move over from the black box model where we're relying completely on a computer to develop a model for us to a more physics-informed, or what I discussed last time, called a gray box model, where we can combine elements of what we know. We know a lot of physics from a lot of our classes and a lot of our teaching. We can incorporate the stuff that we know, which is our physical insight, but the stuff we don't know, like this term, which is really hard to understand, we can use data like this to figure out what that forcing function might be. So let's move over to the gray box modeling.